Why don't we go ahead and get started with our next session? I'm Alice Kern. I'm a PhD student with Vicky, and I'm happy to be chairing this session on a bunch of different multi-wavelength counterparts and follow-up efforts that have been going on. So we'll start with kind of an overview presentation of different models by Ben Margalit.
Thank you. Well, thanks to the organizers for inviting me, and it's great to be back here in Toronto. It's been a while, COVID and all. So we'll hear a bunch of talks that I'm really excited to hear later on this session about, the observational state of multi-messenger, multi-wavelength, I should say, follow-ups of FRBs, and kind of, I guess, my task from the standpoint of the committee, the SOC, was to give an overview of what the models predict. All right, so I'll try to walk you through that through this talk. It'll be somewhat of a laundry list, but the basic of it, I tried to summarize in one takeaway figure. So hopefully that will be kind of the summary. And if you forget about everything else, then just go back to that figure. So before I start, and I've talked about this before in some of our previous meetings way back when, FRB, I don't know, 2019 or what, is this issue of what do we actually mean by an FRB model? Okay, when we talk about predictions for models, what do we mean by model? What is the model describing, right? And there are at least two separate questions. There are multiple different ways you can tackle this, but at the highest level, there are kind of two that are questions that are somewhat separated but also intertwined, right? And those questions are what are they and how they work, right? And you can break that into sub-questions, but the basic gist of it is that the first question, the what are they, is kind of going at what are the sources of FRBs, their progenitors, how do they astrophysically form, in what environments, and so forth. Whereas the second question goes into the detailed physics of how you produce the coherent radio emission and so forth, right? And obviously these two are connected in many ways, but they're also separate. So this is, right, basically separation of source and burst astrophysics. And one way you can look at this is, look at these two different models, right? So here are just a couple of examples for theoretical models for the sources, right? Neutron stars merging, perhaps. Accreting systems like ULXs, plain old boring neutron stars or magnetars, if you will, and ... right? There are many more things that people have suggested. And then there is the issue of how you actually produce the emission. And again, many ideas have been thrown out there. Things like magnetic reconnection, synchrotron maser emission, bunching and curvature radiation, right? And so the point that I want to make here in this slide is that even though you have different sources and different emission mechanisms, there's not necessarily one-to-one mapping between the two, right? A single source can potentially produce different kinds of emission, at least theoretically proposed. Whether or not it actually produces coherent radio emission throughout all these processes is to be determined, right? So neutron stars, for example, people have talked about magnetospheric models through curvature radiation and charge starvation, but also synchrotron masers from neutron stars, and so forth. So, one of these sources can lead to many different models of emission, but also a single model for emission can be tied to many different sources, such as, the synchrotron maser emission, which I think many of you kind of associate perhaps with magnetar models, but there's also ideas of you producing the same kind of emission in different systems, like accreting systems like ULXs, and perhaps merging neutron stars. All right. So it's useful to distinguish between these, right? And the way it goes into the talk or in the conversation about counterparts is to think about these two different kinds of counterparts associated with these two different kinds of models. So people have talked previously in the previous talks about prompt counterparts versus long duration, long-term counterparts, kind of the idea of, looking for supernovae way back when, years ago, or looking for, potentially X-ray or gamma ray emission simultaneously. Rather than use the terminology prompt, I would prefer to use things like, bona fide counterparts, which are bona fide counterparts to the actual burst itself. Each individual burst should produce one of these counterparts, versus associated counterparts, which are counterparts that are associated with the source, okay? They don't have to be associated with any individual burst that the source produces, but they're associated with the environment and the progenitor of the FRB. So that's how I'll call these going forward throughout the talk. So here's the takeaway slide. I can basically put this up and stop talking, but I'll go in a bit of detail into each of these. Okay, so what I'm showing here is basically the theoretical predictions, or at least some of the theoretical predictions for these bona fide counterparts. These are the ones that are currently colored. Okay, and so you see here the red predictions from one flavor of synchrotron maser emission, the blue for a different flavor of synchrotron maser emission, the green for various kinds of magnetar activity, flare activity. And then in the gray, to contrast, you see these different kinds of associated counterparts. And right, this is broken. This basically figure shows you on what time scale you expect emission of these different multi-wavelength counterparts, and at what wavelength, right? So for example, supernovae potentially years before or decades before an FRB, and various other kinds. And I also extended this a bit, the purview from multi-wavelength, and I included multi-messenger. Okay, so I'm also showing here gravitational wave and neutrino counterpart predictions for different kinds of models, just to kind of make it an even more complete picture. All right, so basically for the duration of the talk, I'll just kind of go through these in a bit of a laundry list fashion. So let's talk first about these bona fide counterparts, and I'll start by talking about the maser, synchrotron maser emission, and a particular flavor or variant of the synchrotron maser emission in which these relativistic shocks, which produce the maser emission, run into an ion-loaded medium, a baryon-loaded medium. So this is a cartoon schematic picture with, unfortunately, some Greek letters gone wrong in the PowerPoint, but it doesn't matter. They're not essential at all, so forget about them. But this is kind of a cartoon schematic showing the idea is you basically have some relativistic plasmoid ejected from the source. Forget about what the source is, right? That's a separate question for now. And then this relativistic plasmoid or ejecta runs into slower moving stuff. And in this magnetized relativistic shock, you produce the coherent maser emission. And the idea is that this is a well-recognized, well-understood process for producing coherent radio emission. It surely can and does happen in nature. Whether or not it explains FRBs, you know, that we can debate. And one of the very clear predictions of this model is that in conjunction with this coherent radio emission, you also get incoherent emission. Shocks produce lots of other kinds of emission, and the predominant form in which these shocks dissipate their energy is incoherent emission that peaks at very hard energies, so gamma rays or X-rays. You have very clear predictions from this model, okay? So for example, you can predict the fluence ratio between this hard gamma ray or X-ray counterpart and the FRB fluence. And that comes out to be, you know, of order 1 part in 100,000 or so, okay? So that's a very clear prediction of the model. You can also predict the peak energy at which this hard counterpart occurs, right? So in this case, for these fiducial parameters, this would be at 200 MeV. So this is a gamma ray counterpart to FRBs. And you should see that the latter half of the equation, right, the right-hand side is basically all observable FRB properties, right? So if you observe a single burst, you can just plug in what frequency, duration, fluence, or flux, I should say, and distance to the source if we have a localized source, and bam, you get a prediction, right? And so for most of these extragalactic sources, just because of their large distance, the prediction would be that these counterparts occur at gamma ray frequencies. Unfortunately, most gamma ray satellites are not super sensitive, so that's why we haven't probably detected any of these, even if this model is correct, which of course is a separate question. If you scale down the energies or the distances, right, and you take this to a galactic magnetar, then you find that the prediction is that this should occur at hard X-rays, several hundred keV, which is, you know, smack in the range of where the galactic FRB had its X-ray counterpart. So that's kind of nice. All right. So one of the interesting things that I should point out about this maser model is that you see that the red curve there, right, it starts at gamma rays, but it kind of trends down, and then there's kind of an extrapolation that I put in kind of in dotted or dashed line there. And the idea is that this shock produces emission initially at hard frequencies, at gamma rays potentially, but as it sweeps up through the ambient medium, the shock slows down and the emission kind of moves down in the band to lower and lower frequencies. And so on longer and longer timescales, you could potentially get also optical and radio counterparts on timescales of minutes or hours. Okay, and this is a prediction of the model. You do need to extrapolate a little because you need to assume that the density through which the shock propagates extends many decades further where, you know, after where the actual FRB emission occurs. So it's a bit of an extrapolation, but it's possible. And just to show that, this counterpart, this bona fide counterpart can occur on potentially long timescales, hour timescales, right? So again, just to distinguish between the definition of prompt versus bona fide. You can have a bona fide counterpart to the emission mechanism that's not necessarily prompt, so to speak. All right. So this is just showing what I told you right now. Okay, the frequency kind of drifts down as a function of time. And so if you extrapolate that at longer time scales, you predict potentially minute time scale optical counterparts and hour time scale radio counterparts. All right, next kind of maser emission. So the second flavor of maser emission predicts very bright or fairly bright optical counterpart and is different than the first maser emission that I just described in the following way. The second flavor of the maser model, which is proposed initially by Andrei Belbodorov, is that the shock now runs not into a baryon-loaded dense material, but rather into a electron, positron, right, a pair-loaded wind. And so that changes the predictions. You still get this coherent radio burst, but now the quantitative predictions for the counterparts are a bit different. The physical mechanism is the same, but because you're running into a different medium, it's relativistically expanding, it's pairs instead of ions, you get slightly different quantitative values. And so one of the predictions of this model is that you'd expect, order of second long bright optical counterparts. How bright? You have the number over there, right? So again, comparing the optical fluence to the FRB fluence, a modest maybe factor of 10 to 100 larger fluence than the radio. So not super bright, but there you have it. All right, what next? Well, the last kind of bona fide counterpart to the burst emission mechanism that I listed on the plot that we'll show again later is maybe the most important one, which is this idea of a Magnetar flare. Okay, this is kind of the classic trapped fireball thermal X-ray emission that you get from Magnetar bursts and from Magnetar activity that we observe in our own galaxy. The idea is that you could get this also in extragalactic Magnetars if those are sources of FRBs. And the idea is that basically as you emit this huge amount of energy to produce the FRB, you basically create a pair cascade and you create this fireball that's trapped within the magnetic field lines that produces thermal X-ray emission or quasi-thermal X-ray emission that can also be Comptonized, so you can also potentially get some hard X-rays as well. But that's, basically goes back to Thomson and Duncan, 95, 96, and the very well understood and known phenomenology of galactic magnetars. So I should say that this counterpart is not unique to any individual emission mechanism per se. Many people have associated this kind of counterpart with curvature or magnetospheric models of emission. And this paper, for example, by Wenbin Liu has discussed the galactic magnetar and its X-ray counterpart as being associated or related to this kind of emission. But I should say that in general, any kind of magnetar source that has flare producing its FRB, no matter whether the emission mechanism is within the magnetosphere or at larger distances, should have one of these things. So you should expect, these kinds of thermal soft X-rays, potentially some hard Comptonized component with any model of magnetar model of FRBs, really. All right. Let's go back to this plot over here. So I kind of ran you through the bona fide counterparts. Now what I want to quickly do is run through these associated counterparts, okay? And here are these different ideas for what kind of multi-wavelength and multi-messenger counterparts you might get. So let's run through the laundry list, okay? The first thing that you might expect is that if FRBs are associated with neutron star activity, well, neutron stars are primarily at least born in core collapse supernovae. And so you might expect a supernova to have occurred at some point in the past before this FRB source started occurring, right? It's pretty clear. We know that neutron stars are born in supernovae. Here's the Crab Nebula. And I think all of us are familiar with this, right? So one of the constraints that you can place is basically you can think of, well, how long before I see the FRB could a supernova have occurred, right? And that goes back to actually what was just discussed by Jeff in the previous session and Yuri's question, right? Basically, the environment around the progenitor initially is very dense because you have this supernova ejecta expanding. And so you might worry about the FRB propagating through this dense material and suffering free absorption or accumulating a lot of dispersion that might, not be consistent with, say, what you think the intergalactic dispersion might be to this source. Well, okay, how do you evade these constraints? If you want to evade these constraints and want to have this supernova ejecta optically thin, it turns out that you need, for a typical supernova, to wait of order a decade, anywhere from 10 to 30-ish years, depending on parameters that you assume. So not that it's impossible to get around this, but at least the naive expectation is that you wouldn't think that you would be able to see an FRB, immediately after a supernova occurred, or even as short as a year after a supernova occurred. But maybe if you look in archival data 10 or 20 or 30 years ago, that might be possible. Of course, then you might worry about false chance coincidence associations. All right, so that's one of the constraints that you can place. Then you can think about whether there are other kind of unique diagnostics, right? So you might think about, well, is there anything special about this kind of supernova that might make it more of a smoking gun? Well, people, myself included, have suggested the idea of superluminous supernova being associated with these kinds of events. I think that's not super favorable now, given what we know about the host galaxies, at least not for a majority of the sources, but maybe for some subset. Same applies for long GRBs, which live in similar environments in terms of their host galaxies, right? And would be associated with broad-lined 1C supernovae. So that's kind of the state of things in terms of the optical or supernova. So in terms of the long GRB, right, the reason you might think that long GRBs are associated with such events is that they could also potentially be a channel for forming rapidly rotating magnetars. And again, these are at least promising from a theoretical point of view candidates for FRBs. And the same kind of considerations apply. All right, so from long GRBs on to short GRBs. What do we know about short GRBs and why might they be associated with FRBs? Well, one idea as to why short GRBs could be associated with FRBs is that potentially, well, we know that short GRBs are associated with neutron star mergers, right? And therefore with gravitational wave events that occur simultaneously with these mergers. And there are different ideas for how you can get emission or FRB emission in these kinds of mergers. Some ideas invoke the concept of basically the interaction between the magnetospheres of the neutron star as they spiral towards each other. And so in these kinds of models, you'd predict basically an FRB precursor, an FRB that occurs, or maybe a few successive FRBs that occur right before you might detect a gravitational wave event, okay? That's one kind of model. But then there's another kind of model, which is potentially these kinds of mergers in some cases, maybe rare cases, but in some cases can produce a long-lived, stable remnant neutron star that survives after the merger. And if it does, then, you've basically formed, kind of a revived, heavy, massive neutron star, potentially a magnetar, in a way that is not through core collapse. So again, you might think, well, how soon after this event could you see FRB emission from these kinds of events? You have to worry again about the FRB propagating through the stuff ejected in the merger. In this case, it's not a supernova ejecta, it's the kilonova ejecta, basically, right, the stuff that's tidally shredded from this merger. So it's much less dense, much less material, more rapidly expanding, but the same idea applies. And in this case, the constraints are that you need to wait of order weeks or so in order to see FRB emission. So, anyone claiming that you might have had a gravitational wave or neutron event or neutron star merger occur and have seen an FRB a few hours or days later, I would say that that is hard to do just given these constraints. Not impossible to get around, but this is pretty hard. And there's the idea of the precursors, which I just told you about, right? So these would actually occur before the gravitational wave signal, even though from an observational point of view might detect them later because of dispersive effects, right? The radio propagation, the radio waves are delayed in their propagation through the IGM. And so you actually might observe this after the merger, but in principle, physically, it happens prior to the merger. All right, and then the last kind of associated counterparts that I want to talk about, right? These counterparts that are associated with the sources of the FRBs are these persistent radio sources, right? Which a lot of us love and are looking for more of. And so there are many different models for how you can produce these persistent radio sources. But I think one model that many people have worked on, myself included, and that is at least somewhat favorable, is this idea of a magnetar pulsar nebula, so to speak, right? And so that presumably should form some kind of compact nebula that could produce and probably does produce bright radio emission and potentially can describe some of these PRS sources. And so that's, again, another associated source that would tell you that potentially within this framework of the model, at least, a neutron star or a magnetar model for FRBs, at least a young one, could be associated with these kinds of PRSs. The last one, actually, so the previous one wasn't the last. I forgot about the last associated counterpart, is X-rays. Okay, and again, this idea that you can potentially produce FRBs, for example, through synchrotron maser emission in accreting systems, and in particular in X-ray binary systems like ULXs. And so, right, an obvious prediction from this is that if at least you had enough sensitivity, you could potentially find, right, an X-ray binary or a ULX, co-located with sources of FRBs. Of course, at extragalactic distances, that's very hard to actually constrain, but maybe with the most nearby sources. More speculatively, maybe you could get a kind of optical infrared transient, kind of like a luminous red nova that occurs weeks or years after the FRB source turns off. And this just has to do with the fact that to get the most luminous of these kinds of events within this framework, you need systems that are accreting at hyper Eddington rates, and that can lead to unstable mass transfer. And so you can potentially have a stellar merger of sorts, and that can produce these kind of dusty infrared or optical transients. But that's more speculative. All right, I'm probably over time, so I'll leave this as my summary. We've basically talked about different kinds of counterparts, right? These associated counterparts that tell you something about the source versus these bona fide counterparts that tell you something about the emission. And, I encourage everyone to go after all of these wavelengths and messengers and at all of these timescales to see what we can learn from that. So thanks.
Great. Any questions for Ben? Yeah, Masood.
Do you have a favorite model?
Do I have to pick one?
Like just a speculation?
I mean, I think it's no secret that I'm, biased towards synchrotron maser models, worked on them. So I think I can give arguments as to why I think they're favorable. And I think the galactic FRB event is, to me at least, the best smoking gun that we have. A, that FRBs are, at least some FRBs are associated with magnetars, and B, that, specific predictions of the maser model, like the contemporaneous X-ray counterpart in terms of its fluence and peak energies and things like that, match the model predictions. I think that's pretty strong, but, it's one event, so we'll see what happens if and when we get more.
Yeah, Jacob.
Great talk. In the model that that you and Brian and others came up with, sort of inspired by CHIME data, the toy model, do you feel that that observational evidence is enough to sort of put relativistic shock models sort of at the forefront of potential FRB progenitors?
In my mind, so I would guess I would defer to the previous question in saying that in my mind they were already at the forefront. But I think the stronger argument is the galactic FRB event. I think, toy model of explaining the differences between the repeaters and non-repeaters. I mean, I think there's some good ideas in there, but I wouldn't say that I wouldn't use that as, strong evidence to favor one model over another.
Thanks.
Yeah, I know we talk a lot about volumetric rates and comparing them to cataclysmic models for FRBs. But I was wondering if that could be how it could be used to inform non-cataclysmic models of FRBs, like in terms of the relative, prevalence of FRBs versus other things.
No, great question. So all of these models, right, all of these associated counterparts, if you will, are associated with some kind of formation mechanism, right?
Yeah.
Neutron star merger, say, leading to a stable neutron star. Those are rare events. It's probably unlikely that they explain most, the majority of the population. If you really stretch kind of the parameters, you might get up there, but that would be a bit of a stretch. So all of these are constrained by rates. Of course, you have wiggle room in the rates from a theory standpoint in that you don't know beaming fractions and things like, how long the engine survives and operates. So you have fudge factors to work with, but yes, all of these are constrained by the rates, varying degrees.
I don't know, like when we discuss rates, we always talk about rates above affluence, right?
Yeah.
Which implicitly means rates above a certain energy. So I
Right.
guess the question is to what's the minimum energy you can have for an FRB?
What's the minimum energy? Oh, I see. I would say that within the Maser model, at least, there is no minimum. You can produce, that's just set by the flare energy. So if you have low energy flares, then you get low energy ones. If you have high energy ones, you have high energy ones. If you want to put the Maser model within the framework of a magnetar, then you have an upper limit because you can only, use up so much of the magnetar's internal energy, magnetic reservoir of energy. So that's an upper limit, but I wouldn't say that there's necessarily a lower limit.
Yeah, next question from Vicky.
There's been some evidence, or not evidence, there's been observations of really, really short FRBs, microseconds, and those are all in targeted observations of repeaters, but they hint that there could be vast population of really, really, microsecond FRB. I was just wondering what you think about that.
Yeah. Those are really interesting, and those are very hard to explain within some of these models, especially the Maser model. I mean, you can do it, but you're really pushing the parameter space, right? So time scale in this framework is associated to the Lorentz factor. You need very relativistic velocities to get microsecond time scales. So I would say that's one of the most, to me, that's one of the most important pieces of evidence that is, doesn't jive with this model. Yeah.
And then the last question from Terene. We'll take the one online after, and then, yeah.
I'm curious if you've looked at the second FRB with a PRS in the context of your ion electron models.
Great question. I have not. I have considered doing so, but I have not.
Okay. And then last question from Mohit, if you just want to go ahead and unmute.
Hey Ben, nice talk. Choose whatever question you want to answer. I'm sorry, I just posted a couple of them. I think first one might take more time, so I'll go with the second one. So is there any FRB model that actually predict any millimeter wave counterpart? It might be prompt or even afterglow.
Yeah, great question. So the Maser model, as shown here in the schematic, right, would pass through the millimeter bands on, hour timescales or so. Right, the whole idea is that basically the shock, at least if you extrapolate the shock to larger distances, it slows down, the emission goes down to lower frequencies, and so potentially it would pass through the millimeter on, hour-ish timescales. That is prompt, though not really prompt. I don't know what you want to call it. So it's a bona fide counterpart, right, associated with the burst mechanism, but yeah. And as far as I know, the other mechanisms do not have clear predictions. I should also say the Magnetar Nebula, the PRSs, do have predictions for millimeter or sub-millimeter emission. Yeah.
Thank Ben again.
Thank you.
Great. Up next, we've got a talk on some optical follow-up by Daichi Hiramatsu.
Yep. So I'm Daichi Hiramatsu, a postdoc at CFA. So I'm an optical observer, mainly working on supernovae or any other explosive transients. So, but then I recently started thinking about what we can do for the FRBs using optical wavelengths. So that's what I'll be talking about in this session. So let's see, let's get started. It is working, right? Yeah. So, of course, everyone knows there are quite a few theories for like, you know, the FRB progenitors and then also emission mechanisms. But what's interesting to me is that some of them predict transient multi-wavelength emission, and then some of them are actually in the optical. So that's what I'm interested in the most. And then, like, you know, Ben already introduced this model, so I don't have to go into the details. And yeah, there is a X-ray detection from the galactic magnetar, but this has been the only non-radio transient emission from any FRB sources. So Ben slightly mentioned that it could cascade down to optical wavelengths. So this is the expected light curves in optical, color-coded by, in this case, we are assuming a constant density. So this is color-coded by the, if you assume a constant density distribution around this compact source, the light curve is characterized by two parameters, which is this density of the external medium, and then also the flare energy. So in this case, these color code, these light curves are made with fixed flare energy, and then color coded by the external density. And then if you fix the external density and then color coded by the flare energy, this is how it looks like. So depending on these parameter choices, the light curve could, you know, show really like wide variety of expectations in the luminosity and then also for the time scale. So maybe like, you know, for the case with a really high flare energy and a high density, you might expect to see an optical counterpart. So that's really interesting. So that's what I mean. That's what I've been working on. So for this first study, we just focus on the really well-localized FRBs, repeating FRBs. By saying well-localized, those are localized within 2 arc seconds so that we can actually perform force photometry on the optical images to get the meaningful limits. So this is the sample, including like, you know, most of the extragalactic FRBs and then also the galactic magnetar. And then CHIME has now been, you know, producing these real-time alerts. So you can monitor the FRB activity, and then even for like new FRBs, you can get these alerts, and then you can decide if you want to start, you know, really prompt optical follow-up or not. So there are 2 ways to do this. So having real-time alerts, you can react to each individual FRB, but then that would, you know, you can only do that with some delay because you have to request the TO observations. So the first test you can do is about like a, you know, 5-minute delay after the first radio burst. But then if you know a particular FRB is really in the active phase, you can actually observe the same patch of the sky with the CHIME and then hope for the simultaneous detection there. So those are the 2 main strategies for doing this optical follow-up. And, you know, we are doing this with the CFA telescopes. So one is 1.2 meter Kepler cam, which is, one is the Kepler cam on floor 1.2 meter telescope. So this is robotic. And so like, you know, you can trigger this pretty much anytime you want. And then this is in Arizona. So the CHIME field of view is always visible from this telescope as well. And then another is MMT. So this is a 6.5 meter telescope, so much bigger. And then it has a binospec, which is on the Q system. So you can also request a TOO there. And then you can also like, you know, search any possible optical counterparts in public surveys like ZTF and Atlas. So by combining this data set, we compile the largest, like, you know, compilation of optical limits, including our observations, public surveys, and then also in literature. So this is a really busy plot. So you don't have to focus on the details, but the left panel shows time before burst, and then the panel shows the time after burst. And then each row corresponds to a different band in the optical, starting from G, C, R, O, I, Z bands. So getting from bluer to the redder bands from top to bottom. But I just want to focus on this particularly interesting FRB 220912A, which was found last year, and they have, you know, found to be really active. So the estimated burst rate was about 100 bursts per hour or even more. And then this is quite nearby from FRB. So this is at the distance of 344 megaparsecs. And then here I'm showing one Kepler cam image on the left, which was actually, so this exposure covers CHIME detection. So this is simultaneous with the CHIME detection. And then the middle panel is the reference image from Ponsters. And then the right panel is the difference. So there's nothing there. So all of our observations are limits. We didn't detect anything. And this is just a timeline showing we got 13 simultaneous observations in optical with fast radio burst detections. So that's quite a few. And then, like, you know, our Kepler cam and then the our Kepler cam, LCO, and binospec observations. So these really prove the deepest optical limits to date. For, I mean, by saying deepest, for simultaneous optical limits. So how can we use these limits to constrain the models? So one way to use this is to, you know, compare this with the fast optical burst models. So these are like, you know, coming from inverse compton scaling from pulsar magnetosphere, pulsar winds, and maser outflow. And then these are on the order of FRB timescale. So like milliseconds to maybe up to seconds. And here, our exposure time is longer than the timescale of this fast optical burst. So you have to normalize, we have to normalize the flux by the expected optical duration. So here I say if effective flux limit in the optical is the flux in optical flux limit over entire exposure times, normalized by the exposure time divided by this duration of the optical counterpart. And then this is showing the 4 FRBs in our sample that has been observed simultaneously in the optical. But this is again a busy plot. So I just summarize here that the y-axis is this effective optical flux limit divided by the radio flux, actual observed radio flux from FRB. And then the x-axis is the optical duration. So there have been, there's no pointer here, right? Okay, so there have been like, you know, few cases for the distance one, for the case of like 121102 and then 190520B. So, and those don't really touch the parameters, model predictions, and then model predictions are showing by the, you know, rectangular region. And then our observations for the 220912A actually starts to prove this parameter space for the first time for the extragalactic FRBs. And then these limits are only an order of magnitude larger than the, like, you know, one limit that we have for the galactic magnetar. So we are getting into this interesting regime that, you know, actually we are getting into the, you know, parameter space that's expected from some models with the fast optical, you know, emission. And then we can do better with the fast readout cameras. So one of them is using like, you know, Allo Pocket camera on Gemini. So this is a really fast readout camera. You can read out every like 10 milliseconds. And then since this is on an 8-meter telescope, you can go deep as well. So this is shown by, you know, this gray shaded region or the whole sample that we have. So, you know, you can even get down to like, you know, the improvements is, you know, about 4 orders of magnitude. So with this, we can like, you know, even get to the parameter space that's expected from this maser outflow model. So this is really exciting. And then we just put a Gemini proposal to do this kind of observations for the sample. So fingers crossed. And then Ben mentioned synchrotron maser models. So those are afterglow models that you'd expect, you know, longer duration in the optical counterparts. And then this is showing the constraints for each of the FRB sample, but I just want to focus on the case of this 220912A. So the y-axis is the external density, and then the x-axis is the flare energy. And then the points are these parameters extracted from the radio burst information. So like the FRB fluence and then the duration, you can estimate these points. And then the shaded region, orange shaded region, is the constraint from the optical limits. So if you assume a constant density distribution, some of the points are actually within the parameter space that's excluded by the optical limits. So these are unlikely caused by Mesa model with a constant density distribution. But if you invoke more complex density distribution, maybe this is not the case, maybe. But then, you know, again, you can do better with our pocket. So this gray shaded region shows the predictions with the out pocket observations. And then, you know, if you can do this kind of observations, you can actually rule out the whole parameter space that's expected from the fast radial burst observations. So yeah, I think we are really getting into this interesting that, you know, where we can actually use these optical limits to constrain the models for the FRBs. So this is just my summary slides, and I'll just leave it here. But I just want to highlight the final point that this was only possible since the CHIME produced these real-time alerts publicly. And then the CHIME observing windows are also public. So you can time it. And then, like, you know, this was only possible with that information. So I just want to encourage all the FRB, like, you know, discovery efforts to produce this kind of public information. I know it's a lot of work, but this really enhances the multi-wavelength follow-up strategies. So with that, I'll just finish, and thank you for listening.
Yeah, Casey.
So the FRB emission is beamed, right? And so we see a very small fraction of all FRB sources that are in the local universe. Can you make predictions for how often you could find a fast optical counterpart for FRBs that are not beamed at us?
Oh. So we are just only doing the FRB follow-up. So those are only the beam sources. So I don't know, to do that, I think you have to do the blind surveys, like, you know, Jeff, you know, talked about in the previous session. So I don't have a good number there.
In principle, the beaming fraction could be very, very small. And so there might be very, very many of these that are only detectable by the optical counterparts.
Yeah, that's possible. Like, you know, so people are talking about similar thing for GRBs, right? It has to be pointed towards us. And then if not, you don't see the, like, you know, GRB, but you see fast optical, like, you know, transients. So I think that's interesting too.
Yeah, Ben.
Comment to follow up on Casey. The models that do predict optical emission predict similar beaming as the radio, so you wouldn't expect to see it off axis. Yeah. Sorry.
Maybe a question in the chat. Mohit, do you want to unmute and ask your question if it's from you?
Sure. So I have this question. You showed this external environment, ambient environment electron density versus flare energy plot. I was just wondering whether you take into consideration free absorption constraint and what sort of radio efficiency factor you assumed in your calculation. And I asked this question because Ben just discussed that I suppose it's better to use optical versus radio efficiency factor rather than X-ray versus radio. So I just want to clarify on that factor. Thank you.
Yeah. So the efficiency is we just assume a fiducial, which is, I forgot the number, but it's So we are just assuming the fiducial number there, and then
And okay, and what about the ambient electron density? Are you taking into consideration the free absorption and other effects? Because I see you have 10 to the power 4 unit densities cube, centimeter minus cube values as well. So I thought that that won't be possible if you assume FRB is detected in the chime band.
Yeah, so no, we didn't take into account for the free play absorption here. Yes.
Okay, thank you.
Great. Okay, let's thank Daichi again. And then up next, we've got Paul Scholz talking about X-ray follow-up of some FRBs.
Okay, there's my slides. So, well, not the first slide, the second slide. Oh, I can't go back yet. There we go. Okay, thanks, Biggie and Alice. So I'm going to talk about high energy follow-up of FRB sources. The prompt from, in the organization committee was deep, rapid follow-up. So I kind of approach it from that side. I'll talk a little bit about follow-up strategies, what current limits are telling us, and then what might be different in the era of sub-arcsecond localizations. So what do we mean by counterparts? I guess this is a different way of cutting it than what Ben was saying, but this is my way of cutting it. It's basically time scale. So short bursts that could be prompt at the time of the FRB tied to the directly to the emission mechanism of the FRB, or otherwise you could have bursts that are occurring from the source at other times. And then you have something that's more longer lived and potentially delayed, like an afterglow following the FRB. And then you have something, a persistent source that is always emitting. Potentially it's brighter at the time of the FRB. So it's a good time to look at it. And then when it goes to going after these counterparts, the strategies that we employ in high energy is untargeted and targeted. So untargeted, you have wide field monitors like Swift Burst Alert Telescope and the Fermi Gamma Ray Burst Monitor. Those are great in that they see a huge fraction of the sky. So if a FRB go off with an extremely bright counterpart, maybe they'll be able to catch it. But they can't go as deep and drill down as much as targeted telescopes like XMM, Chandra, NuStar, NICER, that we can point at the location of a source. Of course, we have to know about the source ahead of time to point it, unless we're doing something like the co-observing or shadowing, like Jeff was talking about for deeper, wider, faster. Targeting a known source ahead of time means you're targeting repeaters, so that's biased towards a certain class of source. And yeah, so we want to, well, I'll get to that later. So we have an X-ray counterpart from at least an FRB-like event. So this FRB was came from a magnetar within our galaxy. In a few days, it'll be 3 years ago. It's exciting. And we detected it in CHIME, and STARE-2 detected it as well. And it had a counterpart detected by Integral, the plot is shown there, but also several other X-ray telescopes that were observing it, X-ray and gamma ray telescopes that were observing the magnetar at the time because it was in a state of outburst. And so to put this in context with current limits, here's a plot of the energy in a soft X-ray band for SGR 1935, that April 28th, 2020 burst, along with all the a big sample of bursts and flares that we've seen from our galactic magnetars that Aaron Perlman and I have put together for a paper coming up. And so we placed a couple more things on here. So bursts from accreting X-ray binaries, type 1 X-ray burst, as well as for context, the energies of short gamma ray bursts. And then you can see where the limits lie now. And so these are for targeted observations using telescopes like Chandra XM and NICER. They all have tilde about the same fluence sensitivity set by the effective area of their telescope. And then basically what moves these lines down is the distance to the source, or if you're stacking multiple bursts and making the assumption that there's a bright X-ray event at the time of every FRB, you can move them down in that way. So really, if we want to go deeper, we need closer sources or bigger X-ray telescopes, which we'll get, eventually. And so if you talk about what the distances we might detect these with current generation of X-ray telescopes, we're really brushing. The laser pointer doesn't do something here, does it? We're really brushing like with something local to us, like an M81, or Andromeda would be around the 1 megaparsec line there, a bit closer than that. We can really probe giant flares, but we're only brushing like the more run-of-the-mill bursts that we see from magnetars and from X-ray binaries. We're still a couple or an order of magnitude there away from the energetics of SGR 1935. But you shouldn't despair too much, because if you look at the efficiency, radio to X-ray efficiency of what SGR 1935 is, and you apply it to the FRB energetics we see, you can, kind of hold this histogram to the left, and potentially the magnetars or whatever physical mechanism is causing these could go into things that you could detect at 100 megaparsecs. And then so we can look at this in that kind of parameter space again, or the parameter space of X-ray to radio efficiency. And if you're cutting down into this parameter space, so shown here is limits. Now, I don't show histograms because, all those other sources from magnetars don't have radio counterparts. Some of them do, actually. So, well, anyways, obviously SGR 1935-1 does, so it's shown there. And you can see limits at gamma ray at the top there and soft X-ray near the bottom. There are still, a few orders of magnitude from hitting the X-ray to radio efficiency of SGR 1935, as well as the levels that Ben was talking to us about in the synchrotron maser models, around 10 to the 4, 10 to the 5. But you can see here that the ratio is independent of distance. So really all you need is a bright FRB, and you don't care where it is. I mean, a source closer to us is potentially brighter, but you could get something, a Kilojansky burst from, 1 gigaparsec and be able to place a limit like this. So what we want to cut into this parameter space is brighter FRBs. And again, if we had bigger telescopes, that would help too. So some projects kind of along these lines going on in CHIME FRB well, in this case, it's targeted follow-up, so it's focused on repeaters right now. So the source in M81, Aaron Perlman and I have a bunch of X-ray data there with some simultaneous with some radio data, and we're working on the limits there, and a paper should come out hopefully not too far in the future. And then as well, I've got a project with Amanda Cook where we're looking at the superactive FRB 2022-0912A, where we reliably are detecting like several bursts per day in CHIME. And so in the fall, we got a bunch of X-ray data. And so there you could have, perhaps a rare bright burst from the source, Or we can also stack all the data around the time of the FRB burst for that large sample of bursts and maybe eke something out, replace an interesting limit. Another direction I'm going involves SwiftBat. And so SwiftBat has this capability called Guano, where the bat dumps its ring buffer from an external trigger. And so it ingests external triggers, including from CHIME, the VOEvents we put out. And so working with a Toronto undergrad, we've looked at these bat dumps for hundreds of CHIME FRBs and working on turning those into limits. I mean, I'm talking about limits, so you can tell that we didn't detect anything, but and then coming from another direction is Alice flipping it around, looking at the time of GRBs for radio emission, what we know of radio emission from CHIME at those times. Go ahead next. Okay, so in the era of sub-arc-second localizations, something can change in our strategy going forward. So we will have localizations. The more classic interferometers will get us arc-second localizations at the time of detection, hopefully, like, right away. And then for CHIME, we will have hopefully fairly, as close as we can to the time of detection, an arc-minute localization, and then the interferometric localization will come together when we bring all the data together and correlate it. And so what this gives you for follow-up is the localization gives you a host identification and then a distance to the potential X-ray counterpart. And so if we want to target these rare gems that tell us a lot about the energetics, or will tell us a lot about counterparts, so the really bright FRBs or the nearby ones, and we want to target one-offs, we need to be quick. And I don't know what it looks like in other surveys, but in CHIME, our current strategy is either targeting repeaters that's been localized by someone else, usually, and then scheduling a simultaneous campaign between radio and X-ray observations. Or if we're finding something nearby, there's some human elements in identifying a nearby source, getting that localization, and then checking to see if it has a nearby host. So to really get to capitalize on the rare gems, I think, we have some infrastructure to build to automatically get that localization as fast as possible, check for a nearby host. Nearby galaxy catalog should be fairly complete, and so this should be, quick, and then trigger rapid follow-up. I think that's easier for the classic interferometers that have their localization right away. Maybe it's a little harder in CHIME, but I hope we can get to something like that kind of vision to capitalize on a, potentially one-off nearby event. Thanks.
Great. Any questions for Paul? Yeah, Danielle.
You show us to like the repeater in M81 and the other very active repeater which is farther away. I was just wondering how many bursts you would need from the second repeater to have the same constraint on the M81 as an order of magnitude.
I don't know the number off the top of my head. One thing that bothers me about stacking bursts is you need that counterpart to be there theoretically at the time of every burst, right? If it's something that's only going to be there one every 100 bursts, then it doesn't help you to stack. So it really depends on what's going on. And if you make that assumption, yeah, there's probably an N. I don't know what it is, but.
And also connected to that, if I may, you seem to rely on the fact that the ratio between the radio flux and the X-ray flux is somehow constant. Is that like something usual for magnetars?
Well, you don't have to, I don't think you have to rely that it's a constant. It's just that, you know, if it is a certain value, this is where you would detect it. I think most models, if there's a, you know, prompt or bona fide counterpart, it should be, you know, kind of fixed by the physics. And if it does vary,
Yes,
Ben
sorry, I
will
wasn't-
probably be able to comment better.
Sorry, Paul, I wasn't very clear in my question. I was wondering if the current, the emission of non-magnetars, if this value is pretty constant for a given source. If you have
I mean, I don't know that we really have I don't think we have any counterparts, you know, X-ray and radio co-detections other than from SGO 1935.
Just one more question from Liam.
So it's fixed because it's one data point. Yeah.
Okay, so DSA 2000, Cord, SKA, Krakow, they're all going deeper. So they'll find FRBs that are farther away, making a lot of this pretty hard. But there's also a class of experiments that are sort of all sky monitors like DSA 2000, TRAC, GREX, or not DSA 2000, Burst, sorry, and GREX. So we should have a large population that's relatively nearby. Have you done any rates forecasting, extrapolating from SGR 1935?
No, my, you know, rates forecasting has been thinking in the context of CHIME, which is, you know, getting something local is low. But I haven't thought in the context of those experiments.
Because we do have these upcoming sort of local volume mappers.
Yeah, good point.
Great. Let's thank Paul once more. And next up, we've got Casey Law talking about radio follow-up of FRBs.
Okay, great, thanks. One sec, okay. So, right, so we've heard about high energy follow-up. This will be the low energy follow-up of FRBs. Good. Should it work? No? Okay, good. So I've interpreted that. So this was the title that was suggested to me. And I actually submitted one that was a little more narrowly focused, which is the bulk of the talk, but I'll open with a little discussion of prompt or bona fide counterparts to FRBs and efforts we're undertaking at OVRO to pursue that. And then I'll shift over to the persistent radio source sort of problem and thinking about radio counterparts that are not necessarily transient. So on the first front, prompt radio follow-up, you know, the motivations on this area are to are sort of multifaceted. There are basic questions of, you know, technical problems we would like to fix, localization being one, right? And that motivated a lot of the early work on multi-telescope rapid follow-up, where you want to trigger a second telescope that can localize. There's also the afterglow question, which we heard a lot about, or maybe I shouldn't say afterglow, but more broadly the bona fide counterparts, which can be late time or even precede the FRB. And then there's just kind of fun stuff you can do when you're thinking about ultra wideband bursts. So what can you say with detecting the same burst at different wavelengths, and how can you use that to probe propagation effects and other effects of the burst itself, the intrinsic emission process. And so I just wanted to highlight that at OVRO, we have a number of facilities that are in development and actively observing and interested in the transient problems in general and FRBs in particular. And so there's this code that we're starting to develop, and Jakob Faber is part of this group where we're trying to think about triggers that we can send and support that technically. So DSA will be responding and as we know, to CHIME events, and we're using that as guidance to DSA observing. But there's also things we can do with DSA and the over LWA, which is a low frequency all sky imaging platform, which you can think about, for example, the ultra wideband burst problem. And then we're also very much interested in having LIGO trigger over LWA and having DSA trigger SWIFT. So we have all of these things kind of in development in a number of fronts. And so keep your eyes on in the space in the future. So what I actually submitted a title for was, for this topic was thinking about the persistent radio source problem. So slow radio follow-up, not prompt. And so diving into that, we've heard a bit about this already. The persistent radio sources are these luminous, compact radio counterparts to FRBs. And so the term is very generic, but we're trying to be specific when we think about this. And Liam and I have thought a bit about this as a population. And so we settled on this definition because it was fairly easy to distinguish from astrophysical foregrounds, especially. So, star formation in a galaxy is a luminous radio source, but it's not necessarily compact. And so we want to distinguish it that way. The energy level we've chosen, excludes many transient like supernovae and other classes that might be confusion and astrophysical confusion. And so choosing this definition helps us to think about how to find these persistent radio sources without necessarily having FRBs themselves. And so the two archetypes of this class are these 121102 and 190520. There are others now in play, and people are thinking very actively about how to search for them and identify them in other data sets, which is what I'll sort of dive into here. What's really fun about them, of course, is that, as I mentioned, you can find them even though you don't see the FRB. So that's a kind of a fun angle to it. They should show up in large surveys, radio surveys. And for each one that you can distinctly associate with the FRB sources, you have properties you can extract from the radio emission. So things like the radio spectrum, spectral turnover due to, if it's a synchrotron source, you can see a spectral turnover at low frequencies, which tells you about the size. You can also see how they evolve in time, gives you energy constraints for the source that powers this thing. And that's just, directly by definition telling you about the nature of the source that produces the FRBs themselves. And so, again, Ben and others have put great work and thought into this in this space about using this to make great physical constraints on the FRB origin problem. And so this is this paper I referred to. So Liam and Kshitij Agarwal and I put some thought into this. And one way we tried to go about this is thinking about backing out from the FRB rate, backing out to the source rate, thinking about repetition statistics, and how commonly PRSs are associated with FRBs. And so we have some very loose constraints on that, which allows us to go from the physical volumetric rate of FRBs all the way back to a source rate and then a persistent radio source rate that lets us think about how likely it is you could find these sources in large radio surveys. And some reference numbers here. So we're talking about volumetric rates on the order of, say, thousands, if we're fortunate, tens of thousands of sources and PRSs in the universe, which is something like 1 in every 100 or so star-forming galaxies in the local universe. Okay, so to go about finding these sources and using them to understand the FRB source problem, I've thought of 3 strategies, which I'll just summarize here quickly. One is the pointed strategy. So this is the tried and true. It's what your parents would have done if they were looking for persistent counterparts to their favorite source that was transient 50 years ago. And the idea is that you can use it's very effective because we can use very generic radio interferometers, things like the VLA, and that might be frequency agile. They're very sensitive and pointed, but of course the basic problem is that they don't scale up to large samples, right? They don't. You can't get enough time to pursue all your sort of marginal candidates. You really have to have a good case. But that said, I would say the ideal platforms to go about this, if you can get the time, are places like the EVN, as we've heard about here earlier today, and the VLBA, especially because they get at that compact size that we need to exclude the biggest astrophysical foregrounds, which are AGN, far-forming in the host galaxies. And we have some compelling candidates that we've heard about earlier here today, such as from Meerkat, but still they require this VLBI follow-up to really exclude a lot of these astrophysical foregrounds. And I know that's something that a lot of us are pursuing actively. So strategy 2 is the commensal approach. That was a movie on the top left there, which is not going to play on PDF, but that's okay. But the idea of commensal searches for persistent counterparts is that you have the 2 data streams, right? Or 1 data stream that's digitally sampled and processed in parallel in 2 ways. So there's deep imaging that can happen simultaneously to the FRB search. And actually, this is a pretty common approach to doing FRB search nowadays because we want to get lots of time on sky. We've developed these commensal instruments to operate in parallel with other people that will point it at, some boring galaxy looking at H1. I don't know what they're doing with it. We want the FRBs, right? And so so we get lots of time on a telescope when we have a commensal instrument. What you give up in that, of course, you don't have the ability to control the telescope, where it's pointed, what frequency it's observing at, and so on. But you do have, one novelty of this is that you have really good calibration, actually, with systematic calibration is quite a difficult thing when you're localizing FRBs. And I find that certainly to be true for the VLA and the real fast instrument. We've been able to leverage the primary data set and calibration against the commensal analysis to improve localization precision. I'll just call out just briefly here, the real fast instrument is one that I've developed at the VLA. It is now a facility instrument of the VLA, so I hope you all apply to use it. You don't need permission from me. Please go use it. I would be very happy if people used it. That's what the status of the project now is. It's now a facility resource of the VLA. Strategy 3 is surveys. So this is potentially, I think, the biggest strategy in the future, and one that I think I'm most excited about. We're really, I think someone probably said this a decade ago. We're in the decade of surveys. I think it's really happening this decade, though. But I think it's only going to grow in time, of course, as observatories like Rubin, SphereX, CHORD, and others are producing these incredible large data volumes that are uniform, systematic, and can do so much for us. And this is also very relevant to the persistent counterparts of FRBs. So we have uniform, unbiased, large, relatively sensitive, but not quite as good as pointed sensitivity. And a good templates for this, platforms for this kind of science would be the VLA Sky Survey. I'm showing a LOTS field coverage here, and which is an incredibly sensitive, low frequency reference data set. But also RAX and others are going to be coming online soon to do even more here. Sorry, RAX is already online, but it's going to be expanding and growing. And there's actually consideration of a fourth epoch of VLAS coming too. So there's a lot that will come in the future. And there's a lot of work in this area, that's already been published and is coming soon. So I want to highlight Danny Voll's work, which came out recently, and Adeze Ibik, who recently published this persistent counterpart candidate for a CHIME repeater. And these are using basically, I think in both cases, really, these are surveys, right? So all of these are survey examples of how you can surveys to find counterparts or try to identify counterparts in large survey data sets towards FRBs. And again, the biggest challenge is astrophysical foregrounds. So the more you can discern, characterize, discriminate the radio counterparts, the better you can say it's astrophysically connected to the FRB phenomenon, right? What that source really is. And that's things like radiospectral index, luminosity, and then understanding the galaxy well enough to say it's not just star formation. Those are all things you really need to do if you want to identify this in a unique way. And I would be remiss if I didn't mention DSA 2000. So this is going to be an incredible platform. It's in conceptual phase right now. The next year will be very critical for the future development and what we can what we're going to build. But the idea, the concept is that we'll be building a next generation large survey telescope in Nevada, which is 2,000 elements, covering from 0.7 to 2 gigahertz band. And it's really built from scratch as a survey instrument. So it's doing massively commensal observations where it can do continuum, polarimetric, spectroscopic surveys, including FRBs and pulsar surveys all at the same time. So the digital system is incredible, and it's actually progressing very rapidly, and we're very excited about what we can do with it. For persistent radio counterparts, I think it'll be incredible. We'll have a billion source radio catalog where we're identifying AGN out to the edge of the universe, say, but also persistent counterparts out to a redshift of 0.1, 0.2. And that's a huge volume over which we can actually, sorry, 0.5, I didn't do the math right. So persistent counterparts in this definition that we've described, we'll find the counterparts at the redshift of 0.5, thousands, conservatively, thousands of these PRSs we found in the all sky catalog. And what's really cool, I think, is that because of the commensal nature, we'll have a chance to find FRBs in the same places we find these persistent counterparts. And we'll actually have millions of H1, resolved H1 galaxies out to a redshift of 0.1 or so with the DSA 2000. So that's a post-galaxy characterization with a redshift with a persistent counterpart and an FRB that's emitted in the same galaxy. That's the kind of stuff you can do with these massively commensal platforms. And this is just one science case, right? This is just about thinking about persistent counterparts for FRBs. So with that, I'll wrap up and take questions. Thanks.
Yeah.
So DSA won't have the baselines to tell those 1,000 PRSs from the billion AGN, will it?
Let's see here. It will not have the resolution to do that. That's right.
So it's how do you get those 1,000? How do you find them?
Spectra would be a big part of it. You can also, the way that these survey programs are working now, where we would measure the expected radioluminosity from star formation in the galaxies. So this star formation, in that case, we can exclude it, but AGN look an awful lot like PRSs. Off nuclear is sufficient. It might not be spatially resolving them to resolve it out, but you can show that it's kiloparsecs off from the nucleus, and that's a big helper too.
Right, and so I guess that probably weeds it down to, I don't know, a number that you can follow up in VLBI or something.
Yeah, what limits you in that case is that galaxies don't often have like a center, right? And so in that case, you get ambiguity. But in many cases, off nuclear luminous radio sources are very distinctive. Yeah.
Great, thank you.
Taranay?
So kind of building off of that question, there's certainly this AGN community that would argue these, PRS and dwarf galaxies are seeds for supermassive black holes. And in some cases, they are offset from the center of the galaxy. So I'm just curious if you have ideas for how one might distinguish between the two.
No, I was hoping you did actually.
Working on it.
I think what's fun about the problem is that anything we find is relevant to wandering black hole and black hole formation problems, but also it could be like a really cool FRB thing, right? So intermediate mass black holes might be the same ballpark where it's physically totally different and exciting nonetheless. And so I think the search problem is really well motivated, but yeah, we need to be real specific about what we're finding.
We'll go to Jason and then Jeff, and then.
Yeah, I was just wondering how many PRS candidates you guys have found in BLAS so far, and whether the discovery rate kind of matches the volumetric rate you were estimating.
Right, I saw this. Yeah, the rate in our estimate was high, I think, and I think it's probably going to come down, honestly, from a combination of factors. But I don't think we're matching it in what we've done so far. But I think it's really hard to estimate because we have an initial campaign, which I showed a figure from, which I'm hoping to write up this year, but we whittled it way down because we started to add things like spectral index and, legacy survey coverage and more, and it really brings its sample size way down, but it's necessary to rule out all these astrophysical foregrounds. And so I don't have any good sense of what the rate is in the end because it's so kind of bespoke, and I'll have to work on it some more.
Okay, thanks.
But background AGN are a big problem also. Yeah.
Thanks. You discussed studying PRSs in dwarf galaxies.
Mm-hmm.
And have you studied their metallicity of those galaxies?
In the local universe, we have all that. I haven't. No, is it not? I feel like
Because if you have a dwarf galaxy, you get a spectrum, and then you can do that, and that's going to be pretty much targeted, especially with dwarf galaxies.
I see. Okay.
And that would tell you a lot, especially if you can even do it with IFU at the location or close to the location. I think that would tell you a lot
about specifically the AGN problem,
or a formation channel or something.
I see. Right. Okay. Thanks.
I think we're out of time for questions. You can ask them during the chat. Let's thank Casey once more. And then up next, we've got Thomas Abbott, and he's going to talk to us about the CHIME FRB VOEvent service.
Hello. My name is Thomas Abbott. I'm an incoming master's student at McGill, and today I'd like to talk about the service, virtual observatory events. So first of all, what exactly is a virtual observatory event? Some of you may be familiar with them already. Some may be familiar with them from other fields. They're public alerts of, in this case, FRB detections. So these are real-time alerts that can be used for follow-up, for outreach, or more. All of the VOEvents come in either a machine-readable XML file or a human-readable email, and they contain basic metadata about the FRB candidate. They can also include additional information, but at the bare minimum, we have some metadata that's included. I'll talk about in the next slide. Sorry. And they come in 4 different types. The first being a detection. The second is a subsequent event, which is an event that we believe is likely a repeater, and retraction in the case of a false positive, and finally an update if a particular value about the FRB candidate has been updated or a new name has been given to the FRB. So in terms of the metadata, all VOEs come with a header, which just includes the alert type, the date that alert was published, and a unique IVORN ID. They also contain what we call a what section, which has 2 things. One, the observatory parameters, including timing and spatial resolution, as well as the observing frequencies of the telescope, and the event parameters such as the dispersion measure, the signal to noise ratio, and the known source name. A quick comment about the name is that we have the ability to submit candidates to the transient name server to get a TNS name. Although, as we've seen today, there may be some more creative ways to name FRBs that we might have to think about. It also includes a where and when, which gives some localization of the event and also the detection time. And then how and a why, which in the case of CHIME VOEs gives a description of the CHIME pipeline, as well as some significance scores and RFI scores for the candidate. And lastly, for repeating events, retractions, or updates, it includes a citation to the prior burst that it's referring to. So just to give a quick summary, whenever I mention FRB VOE, this is the information that I'm referring to. And this was first introduced, the standard was introduced in Petrov et al. By Emily Petrov, who many of you know as the former CHIME project manager, and who's since moved on to the Perimeter Institute for Theoretical Physics. So in terms of the actual service, it's described in this flowchart here. It starts with a detection at CHIME, where an event moves on to candidate status. And once that happens, an actor is sends that event to our VOE database, where the event is saved. And from that point, a comment broker, which is an API that listens for new events, will retrieve that event and publish it to all of our subscribers. And that can be used for follow-up, whether that be localization or multi-wavelength follow-up, or general interest and outreach just for folks who are interested in keeping up to date with CHIME detections. So this service has been active since October 2021. We've published over 1,700 VOEs, now actually pushing more like 1,800. And we reached 100 subscribers from 4 different continents. And I also wanted to bring attention to Andrew Zwaniga, who was a master's student at McGill that contributed a huge amount to the software development behind this service. And he's since moved on to medical physics at TMU. So in terms of our subscribers, we've reached quite a few people around the world. There are subscribers from over 60 institutions and over a dozen countries. They come from all sorts of backgrounds, including amateur and professional astronomers, from undergraduates, graduates, postdocs, and faculty. And they also have a wide range of campaigns, with the primary interest being detection of new FRBs. So some of the challenges we faced since the service began operating, especially early on, there were several cases of RFI storms triggering a large amount of events being sent out. Since then, that's been mitigated through increasing thresholds on signal to noise and on our RFI score. We also have some experience with pesky non-FRB signals, like some pulsars that have been repeatedly misclassified as FRBs, but that's also been largely mitigated by the change in threshold. And an additional challenge that we're working through is we want to make this software as easy to install as possible so that other members of the community can use it. And at the moment, the FRB VOE backend and the Comet broker run on separate servers. We'd like to combine that into a single server just for user friendliness. Lastly, we have some issues with high latency retractions where a retraction will be made and then it may take up to a day after the event has been published for us to publish another VOE retracting that event. So ideally, we'd like to reduce that to several hours. In other words, as soon as that retraction is made. So in terms of future plans and improvements for the service, we'd like to automate the subscriptions and retractions, again, to reduce latency. At the moment, our latency for retractions is typically around 1 day, and our latency for the events is around 20 seconds or so from the moment of detection. But we'd like to automate that at least to reduce the latency for retractions. We also want to create a searchable public VOE database. This could be used by anyone in the community to look through some of the recent detections from CHIME and scan through them to get a better feel for what we've been detecting. And lastly, we'd like to implement subscriber chosen thresholds. At the moment, all the thresholds for what VOEs are sent out are determined by the host of the service. But ideally, we'd like to allow subscribers to set their own thresholds to optimize the utility of the service to their particular campaign. And then this one's a large one, is we want to make the FRB VOE service telescope agnostic so that other radio telescopes and facilities can also use the service and publish VOEs of their own. And this is a tremendous amount of work that Andrew Zwaniga has largely completed, and you can probably expect it in the next few months, although I don't want to give any concrete estimates on when it will be available. There are still a few things to work out, but that's something to look out for. And then this flowchart here describes a typical workflow of the service. So in the far left column, the host can turn on or off the Comet broker. That's the API that distributes the VOEvents. They can also add or delete or get subscriber information. They can submit, search, or change TNS names. And lastly, they can get VOE events to analyze them or publish VOEs of their own. So I'm relatively new to this project, so I'd love to hear your feedback. It could be very useful, especially if you're already a VOE subscriber and there's something that you would like to see done with the service. And in addition to that, we'd love to hear if you're a VOE subscriber, how you've used the service. It's really useful for talks like this to talk about what sort of impact it's having. So if you're interested in subscribing, I'll put this link in the Slack channel. And then you can just follow to subscription requests to find that link to subscribe for yourself. And I'd like to thank you very much for having me.
Thanks, Thomas. So we'll directly follow this with a short panel. So we'll have Jakob Faber, Daichi Hiramatsu, and then online, and I hope I pronounce this right, Omar Ould Boukattine. Oh, phew. Okay, so I'll have each panelist present themselves and we'll talk a little bit about their thoughts on VOE events in the past and in the future. So why don't we start with Daichi?
Yep. So I'm Daichi Hiramatsu again. I just gave a talk, and I use VOEvents for optical follow-up. So there are just two. I think for me there are two main use cases. One is to monitor the FRB activity. So like, I mean, just to monitor the FRB activity. So once like, just to check if any of the FRBs that have been observed by CHIME get into active phase. And then if so, we want to do the simultaneous monitoring with the CHIME observing window. And then another use case is to use the rapid follow-up. So if there's any like, low DM or low DM or high signal to noise events, we can do, once we get those VOEvents, we have a listener set up, then we can like, just request the TOO to like, the telescopes that we have access to with like, 1.2 meter telescopes and 6.5 meter telescopes. And those are my two main use cases for VOEvents. And I think my suggestions for the VOEvents is that one is already mentioned, but, publicly searchable database would be really amazing. And then also like one more thing is that there are like, so detection and then the, wait, sorry, I forgot detection and then what's the case there? Oh, subsequent, right. So I want to see the cases where like, some of the repeating FRBs have detections, not the subsequent events. So I want to see like, this, post-processing on doing this, update from detection to subsequent so that, so that we know those individual, FRB is actually associated with repeating sources. Thank you.
Hi, my name is Jacob. I'm a first year grad student at Caltech. And yeah, I mean, Daichi said it really well. A lot of our use cases are very similar. As Liam and Casey sort of described, there's a lot of use cases and science that can be done with the DSA 110. We've already sort of set up Casey's done a lot of work on this this overall alert system that is not just being used for the DSA 110, but also the LWA. Our situation's slightly different in the sense that we're really just kind of leveraging the coincidence that the DSA is sort of aligned in longitude with CHIME, which is really helpful for us, and the fact that we're at a higher band to kind of take advantage of these VOEvents and sort of look for coincident detections, of which we already have a few. So we're not really kind of a alert and point kind of telescope, but more just an alert and wait or wait on the edges of our seats kind of operation. Again, because the DSA 110 is mainly a transit instrument, so. Yeah, I mean, subsequent alerts are still really useful for us. Currently, we're working on getting an addition to sort of the listening service that we already have set up at OVRO to kind of compare the incoming VOEvents to a known source database from CHIME and compare to the detections that we're making with the DSA 110. So subsequent alerts would help us a lot in that respect. But mainly the VOEvent service is just incredibly helpful for us as a reference point so that we can do collaborative science with CHIME and the DSA to look at everything from energetics to scattering, scintillation, constraining emission physics and propagation effects. All of those are really strengths that we gain from utilizing CHIME's VOEvents. And we're also service of our own that we encourage all of you to subscribe to. It's very close to being fully operational. And yeah, I think the more that we can leverage these VOEvents, the better we can all collaborate with each other on various science cases that that definitely differ depending on the exact pair of observatories that you're using. Like for optical follow-up, obviously the science cases are are very different than for two radio instruments that just happen to be in different bands, but or for an X-ray instrument or what have you. But yeah, regardless, the science that can be done is really, really rich when you have two instruments instead of one or multiple.
We'll go to Omar online.
Yeah, can everybody hear me?
You sound
I
good.
see someone nodding, so that's good. All right. Hi, my name is Omar Ould Boukattine. I'm a first-year PhD student here in Amsterdam with Jason, who is there. And I'm mainly interested in working on, so what I do is I do high cadence observations of repeating fast radio bursts. So when I look at VOEvents, I mainly search for subsequent notices. So when is a repeater active again? And that is also interesting, for example, also in our PRECISE project, which Frans talked about a little bit earlier today. But when I look, for example, at the VOEvents, the stream, the 1800 messages that so far are popping up in our Slack channel, I see that the latest subsequent VOEvent was in November 2022. But then there is the CHIME FRB website, which is also a repeater page. And the latest update from that page is April 2023. So for us, is the most important thing in our research is getting an update on when repeaters are active so that we can subsequently target repeaters. And it's great that these services are out there, and we check those pages, I think, weekly, multiple times a week. But as I can tell right now, I have two sources to check if repeaters are active, and they don't always correspond with each other. So my main feedback, or one of the big points that could be improved in this thing, is if the VOEvents could update us at this in the same manner that the web page is currently updating us. So to always know which repeater is active, so that we don't have to randomly point the telescope in the sky.
Thanks, Omar. And now we can turn to the audience. We've got a few minutes left in this panel session. And so we're hoping to hear if any audience members similarly have feedback on this VOEvent process. Yeah, Casey.
I'm interested in if VOEvents can be adapted for co-observing or predictive observing. Is that sort of shoehorning too much into the protocol, or is that actually something that we could, could you have an event which says not FRB occurred, but that CHIME is about to have a transit of R3 or something like that? Is that sort of thing we can do? Yes. Oh, the answer is yes.
Sorry, I'm trying to remember the white paper, but I think there was something about intent. So we got to check Emily's white paper about that, because the co-observing is, of course, very important. The VOEvents were used to connect aperitif and LOFAR at the same time, but of course that only worked because they were co-observing, because LOFAR cannot see the whole sky. You can just see the tide array, the tile beam. And there it was essential, otherwise we could never have made those detections.
Yeah.
Or actually the non-detection, sorry. We used the standard VOEvents for aperitif to communicate with LOFAR and see aperitif saw a burst just now, and then LOFAR never saw any at the same time. But that was a standard, but beforehand we had an ad hoc co-pointing schedule, yeah.
Just to comment on what Omar is saying, we're of course in CHIME very aware of that issue, and we've discussed it. Just if you want to understand the backstory, it's that the VOEvents, there was effort put in to make them automated, and they're automated, and that has been working pretty well. With, as Thomas said, though, occasionally we have to retract something. But the web page that's not automated, that needs a human to do. And in fact, as we detect more and more sources, the chances of an event that might be a repeater, there's actually quite a bit of statistical analysis you have to do to be sure that is that repeater. And so we haven't really found a great way to automate that. And in fact, that there was a little bit of debate exactly. It's quite an interesting statistical problem to figure that, to know with certainty. And that's a little bit has been the bottleneck for that reason. I don't know, Amanda might want to say something.
Can I follow up on that, Vicky? Hi, this is Aaron. Can you hear me?
Yes, you can.
I'll just say that for that particular case, at least to the extent that I understood Omar, the statistical problem doesn't matter, right? I think it would be sufficient if when the web page is updated, it also submitted a VOEvent, right? And then whatever time, I mean, the fact is that the web page is like 6 months ahead of the VOEvent service, right? So clearly you guys have figured this out, the statistical problem with humans, and whether or not it's automated is a secondary problem to having the services match each other.
Yeah, I believe this is a confusion between the known source database and if we have the correct source name or if it's later identified by the czars. But I'm actually not sure what information from the known source after we pass to the VOEvents. So I think that might be something we should look on offline at.
So another aspect of this is that the VOEvents, they all go out. And so in principle, anybody can recognize the repeater. It can be us, and we can do our best to do that and work on this, but anybody else can also do that from the VOEvent goes out automatically. So if you have a list of repeaters, in principle, anybody here could figure out, oh, is that a VOEvent likely to be a repeater? You'd probably not be 100% sure, but you could, you would know that whether or not it was potentially a repeater.
Justin says the thresholds are different.
We could have an internal collaboration. It's true. The thresholds are different. That is true. So you're worried about faint repeaters not going through the VOEvents. That is true.
Right, and if you're an external, consumer of the events, and you know that these subsequent alerts exist, you might assume, okay, well, here's an FRB, and it came through as a detection VOEvent instead of a subsequent VOEvent, and I'm assuming that CHIME knows more about this event than I do. And the reason it didn't come out as a subsequent is because it's a different FRB, right? So you're trapped in this sort of conundrum of not having enough information to make the decision, given the fact that there exists a channel via which these are supposed to come through and they don't. So if you make it clear to the community that we shouldn't trust the subsequent channel to be complete, then that's fine, and we won't. But then that has to be made clear. I think that would solve at least some of the problem.
Yeah, so consider this clarity.
Okay, I think we're a little bit over time. So as long as people still want to have coffee and cookies, which